discussions, the deliberations were very satisfying to us. Many questions were asked, many things were answered. And as you could see that the discussion is not just a question-answer session, you asking questions, the rapporteurs giving the answers. You can also place your point of view. If something has not been discussed, but yet related to the theme of the session, you can raise those. So it is an open discussion. And in many senses, in that sense, the discussion sessions yesterday were very successful. That's the feedback we got from the participants. Today we want to continue in that vein. And the first session will be chaired by Professor Chiranjib Mitra. I request him to take over.
Thank you, Professor Banerjee. So it's a pleasure to introduce Professor Peter Barker, who is the first speaker of this session. Sorry? Yeah. So let me start the presentation. Yeah, I'm starting the EA. So, where is the folder? Which folder? This one? Yeah. Right. Right. So, to introduce Professor Barker, he is a professor in physics at University College London, specializing in the manipulation of cooling of molecules using strong optical fields with expertise in atomic and molecular and laser spectroscopy, nonlinear optics, laser-induced phenomena, and gases. His work focuses on creating slow, cold molecular gases and cooling them to ultra-cold temperatures. To give a bit of a background, Professor Barker did his PhD in the year 1996 from University of Queensland in Australia. And subsequently, he did a postdoc in Princeton for 4 years. Then he was in Heriot-Watt University in Scotland. And he joined the faculty of UCL in the year 2006. So we had a brief overlap, but we never met. So, and the title of his talk is Macroscopic Quantumness and Classical to Quantum Transition. Professor Barker.
Okay, well, thank you very much for the invitation to talk here. And as many of you, or a few of you know, that I've spent a couple of days traveling in India, my first time, so I've enjoyed that. So it's nice to be able to combine these two things. So let me talk. So you know, in the introduction, I'm sort of I've worked on a range of things, cold molecules being one, but actually for the last 15 years, I've been working in quite a different area, and so I guess I should fill you in on that first to give you an idea on what I'm doing and how that kind of fits with what I'm going to be talking about today. So actually, for about 15 years, I've been actually working on what I would call sort of massive quantum systems. And in my case, these are mostly large particles that we actually levitate using different fields, optical, electric, and magnetic fields. And so we've been using these to really start investigating quantum mechanics and the macroscopic limit. Sorry, I'm just finding the button here for the, I guess it's that one. So these are sort of macroscopic quantum systems, and in fact, these are brand new quantum systems. and we spent a lot of time basically controlling these to get them to a point where we can actually do quantum mechanics with these systems. And so actually with Hendrik, we've worked together on looking at things as, creation of non-classical states, but also looking at sort of wave function collapse mechanisms, or testing experimentalists. So, I'm an experimentalist, so bear that in mind. And so I'm giving really a perspective, an experimental perspective. And I know many of you are theorists, and so perhaps this is, hopefully interesting to you, to give you some insight in the experiments in this particular platform. I'm going to provide a review actually beyond what I do as well, but before I get into talking about specifics, and I'll give you a reason why I'm going to talk about this particular platform at the end, near the end of the talk. Not only do we use these systems for really exploring quantum mechanics in this kind of more macroscopic regime, but we also use them as sensors, and quantum sensors. For example, we're actually using this platform now as a type of dark matter sensor because we can measure forces, very small forces, using this technology. And for example, electric field sensing, accelerometers, and even actually very practical things for particle acceleration, particle characterization. But let's get on to what we're talking about. So what I want to talk about is, how we can go about and how others are going about testing the macroscopic limits of quantum mechanics. And really what I'm talking about here is quantum systems which are increasing in size, but also increasing in mass. And I'll give some examples of essentially large mass, small size superpositions, and large superpositions, large size and small mass. But perhaps what is just as important is the increasing complexity of these systems. So, there are many, many degrees of freedom, and actually controlling these degrees of freedom and working out which degrees of freedom you can ignore is quite important, really, for really establishing these systems as quantum systems, and then actually testing the validity of quantum mechanics. And I'll talk most particularly in terms of the superposition principle. So why would you want to do this? So one thing is really just, gain an understanding of what the transition is from, quantum mechanics to classicality. Are these systems always quantum? Can they never be quantum for some reasons? And then I'm going to touch briefly on how this work then connects to how you might be able to look at testing the quantum of gravity using these systems. And lastly, as I sort of pointed out, this is important also for, so I think it's not just a foundational question of what is, the limits of macroscopic quantum mechanics. I think it also has important for development of quantum technologies. And I think these two things fit together. And, and often when I'm writing a proposal, normally I put it in terms of, well, we're interested in these fundamental questions, but actually there are also these applications that can come from that. And I think as an experimentalist, that's a particularly easy sell to make when you're applying for funding for research. So I guess to start, I should start in 1935. Essentially, we've all been talking about the Schrödinger cat, where basically you have the superposition of an atom decayed or not decayed, which is then mapped onto whether this cat is alive or dead. And, of course, this is, counterintuitive. A cat is a macroscopic everyday object where we don't really observe any quantum nature. And just the fact that it can be dead and alive is, of course, completely counterintuitive. So, and the question is then, we know from photons and atomic systems now, electrons, that, we can make, these are essentially quantum objects. And so the question is, why do we not see it, obviously, on the everyday, on our everyday experience? And is that basically just because we're not good experimentalists, that we can't control these systems well enough? Or, so is it, if we observe no quantumness, however that may be, is it that basically, we just can't control these sources of decoherence? Or is it perhaps more interesting in that, quantum mechanics as we know it isn't complete, and, should there be modifications, should there be new theories that relate to that? And so, so the aim then is really to really keep on pushing to more and more macroscopic systems. And quite often the question is, what is a macroscopic system as well? And how do you compare these different macroscopic systems to make a sort of an overall decision on, whether this is a quantum system or not? So, of course, a good place to start is Davidson-Germer's experiment, where they essentially showed that you could get interference diffraction essentially from an electron beam hitting the periodic structure of nickel. And of course, in this movable detector, they could detect essentially diffraction from electrons, and so that's really the sort of first demonstration. But since then, of course, there's been a huge number of demonstrations, of which I'm partially blocking with this figure here, but this is essentially a superposition, a 1/2 meter scale. So this is a superposition separated by a 1/2 meter in a cold atom system. And essentially, I won't go into details of that, but there are many of these demonstrations. And the question is, how do you? I mean, obviously, you can start with electrons, and you can go all the way to an actual cat. How do you sort of characterize these systems? This, of course, is a well-known interference pattern that you get from a Bose-Einstein condensate. And in that case, this is quite macroscopic. It's on the millimeter scale. But of course, in that case, the mass is quite low. So I guess a good place to start to talk about this is an experiment that I always sort of go back to and think of. And this is this experiment by Dave Wineland's group, where they created a superposition of an atomic ion. And so this, in a sense, is a massive system. So in this case, this was a beryllium ion, so atomic mass of 9. And so just to sort of map out what this looks like. So this is a single ion that has a charge that is maintained as trapped in vacuum, essentially by using both dynamic fields, so oscillating fields, and static fields here, which can isolate this particle. And it's well isolated because it's obviously in vacuum. But of course, there are all sorts of mechanisms that can come into play, and decoherence in this system at this stage, and in most of these trapping systems, comes about due to fluctuations in this trapping potential, and these are fluctuations due to charge on the surface. So in this kind of pioneering experiment, I would say, very clear experiment, basically you create this Schrödinger cat state where essentially you have x1 and x2, essentially positions of the wave packet of this particle that's oscillating in this potential. And then that is entangled then with these hyperfine levels in beryllium here. So these are hyperfine states that are separated on the order of 12, I think it's 12 gigahertz. And so the ability to really couple this center of mass motion with this truly quantum system of this, this sort of quantized system here, enable them to really demonstrate very nicely how you can make and essentially evidence that you actually have a superposition. So in many of these experiments, what's always required is some sort of state preparation, okay? And in this case, you need to essentially take this particle down to the ground state. So this system has a confining potential here, And what you want to really do is take it down to essentially the vibrational ground state of this system. So, so that you get basically a wave packet spread that is the 0 point ground state spread. So, so how do you do that in this particular system? So this is something that is sort of common to all of these systems, and I'll explain a little bit more detail for these more massive particles, where you need to do you need to have some asymmetry in the system to enable you to basically take energy out of the system to get this to the ground state. And this is called sideband resolved cooling, and using the sort of selection rules and excitation in this system, essentially you can continually excite this so that this particle, which is in a distribution of states, you can continually essentially take the system down so that you accumulate all of these particles in the ground state. And I won't go into too much detail here, but essentially between these two levels, you can engineer that using the optical fields and the selection rules in this system. So okay, so once you get into this ground state, so you can move this into the ground state of this system, and so you essentially have this wave packet that's sitting at the bottom of this potential well. And then you can set a pion 2 pulse, and you can essentially, so you have basically a superposition here in this hyperfine state and this hyperfine state. And then you can use another optical field to displace this and create essentially a coherent state that starts to oscillate in this system. And then you can have another pi pulse, which essentially swaps these two states so that you've moved this ground state up here, and you have this displaced state down here. And then you can apply another displacement, so create another coherent state here, and you essentially have this superposition. So you have this cat state here, and so you have a displacement here in this up state and a opposite displacement, and you can control that phase if you want. And then in the end, to read out this state, then you have another pion 2 pulse, and you can look at either one of these populations and look at the interference that you would expect between those two. And so in these experiments, this is what you see. So this is looking at basically the population of the down state, and essentially looking at how this population changes due to the relative phase between these two superimposed states. And from then, you can essentially change this phase and read out an interference pattern here. So just to give some context, so this is a relatively large superposition. It's 80 nanometers, and it's much bigger than the ground state spread, which is this wave packet spread, which during the time of this experiment doesn't evolve much beyond the 7 nanometer ground state spread. And so this is a macroscopic superposition in some sense, or at least it was at the time. So this is a mass of 10 to the minus 26 kilograms. So it's massive compared to an electron, but it's not particularly massive. And I'm not showing it here, but essentially, what they showed is that if you increase the separation between these two states, then essentially decoherence increases, and the coherence of this system decreases. And this is typical, right? That as you increase the separation here, or you make it more macroscopic, then decoherence processes usually come in. And in this case, it's quite well known, and it's been quite well established that those decoherence processes is essentially charge. And by taking these experiments, these experiments and others at the time are basically the basis of a really important quantum computation system using trapped ions. Okay. So as I said, how do you compare all of these different systems? There are squids, so superconducting quantum interference devices, which are superpositions of current. there are interferometric experiments, standard sort of diffraction type or experiments, which I'll talk about next, that are some of the most macroscopic in some sense. There are these optomechanics experiments that I'll talk about as well, and the question is, how do you go about comparing this? And this is a field in itself, and I'm not an expert, but so I think Tony Leggett was the first to really discuss this. But what I'm going to talk a little bit about here is work by Stefan Nimrichter and Klaus Hornberger, who really have put this, have really applied their idea of macroscopicity to a range of systems. And so it's sort of experimentally attractive in that you can compare your experiment with someone else's experiment. And the essential idea is that there's, if I perform an experiment, there may be some minimal modification to quantum mechanics. So basically here, this can be sort of seen as some sort of dissipation, which in their case takes into a wide case of scenarios. For example, takes into account collapse models. And Hendrik, I believe, will actually talk in detail about collapse models. And the idea is that you essentially, you can compare your experiment that will rule out some minimum modification to this sort of standard, von Neumann equation here. And this basically relates to coherence in the system, but it takes into account, the size of the system, and the complexity of the system in some detail. So I think if you're interested, you should go to this paper and explore it, because this has now been kind of applied to a number of systems, and it's a good way to make a comparison between an experiment that has been done, but also that you might want to do. And so this idea of this macroscopicity scales as the log of this coherence time of the system compared to some reference. And in particular, this is an expression derived for interferometry experiments, which I'm going to talk about next. So just to put this, just from this paper, you can look at this measure here of macroscopicity and look at some of these systems. So there are oscillating membranes, for example, a very large squid, which doesn't exist, Talbot-Lau interferometry, which is what I'm going to talk about next. And to date, this is considered to be the most macroscopic experiments that have been done. So, but what I will eventually get to, so I'm going to talk about these in another experiment that really have extended this, I think in a fairly clear way. But then I'm going to talk about the future really in terms of, and the sort of things that I'm working on and Hendrik is working on in these much larger particles and looking at sort of non-classicality and particularly interferometry in those systems. So let's just have a quick look at this. So this is probably the experiment that everyone is familiar with, and I'll just go over that again for those of you who aren't. And this is actually something that Hendrik had worked on, actually doing a postdoc. And so this is in many ways, it's not a standard interferometry experiment, but it's a kind of interferometry experiment that you can easily recognize. It's it sort of has a very good optical analog in that sense. And so this is now interferometry of these very large particles. So zinc, I had to write it down because I couldn't remember it, zinc-coordinated porphyrins around a tetraphenylmethane core. So, and so these are molecular systems that have been engineered specifically for these experiments. But the important thing about this is these exist at different, internal temperatures. They exist at different conformations. And yet, as long as you can select a particular mass and do an experiment on a particular mass, then, you can see an interference. So you can see the fact that there is still superposition even for these larger particles. So if you look at now this mass, this is going from 10 to the minus 26 to 10 to the minus 24. So this is a significant jump. And so how does this work? Just so, just to point out that it's different. So this uses this Talbot-Lowe effect, essentially, where the grating here for a quantum mechanical interference is replicated at this Talbot length. And so what you do, so there's essentially 3 gratings here. These are 266 nanometer separations. This grating actually does a type of collimation of the beam to start with. And then the interference occurs on this grating, which is an optical grating. So these are so large that you couldn't really quite easily use a standard grating. So this also has a period of 266 nanometers. And then there's a third grating also at this same fringe spacing, which you translate across the beam. And this is important because what it enables you to do is to map out this spacing here, and you don't actually have to really look at, you're looking at essentially all the particles that are coming through this particular grating here. And so what you see as you tune this is that you get this fringe pattern, which basically tells you that you're seeing this effect. And I'll show you the results of that. But what's important is that this system has many masses, and what you need to do is choose one of these masses, and that can be done by essentially doing an ionization process and just detecting a particular charge to mass ratio, which gives you that. And so these are beautiful experiments, but incredibly complex experiments. And so this is work by Mark Hassan's group primarily in Vienna. And they've been moving through this progression of larger particles. And my understanding is that actually, so this is the 25 kilodalton limit so far, but that will get much larger, and they're doing work on gold clusters. And so there is the expectation that there should be interference using a similar device with much larger systems. And so that's something to look forward to. And so so this is the interference fringes that you see as this final grating is displaced across the Talbot-Lowe pattern. And what they do then is really to look at the visibility of these fringes as a function of the laser power. So the laser is doing this diffraction via optical forces, and you can measure this visibility. And what you see here is this is what you would expect classically, and this is what you would expect from a quantum mechanical model of this situation. Coherence times here of 7.5 milliseconds. And when you put this into this expression for the macroscopicity, you get about 14.1, which was consistent with the estimations made by Nimrichter and Hornberger. Okay, so let me move to a completely different system. So given the amount, there are a huge range of systems that I could talk about, but I've just sort of chosen these two because they're close to this macroscopic limit. But for example, this one, which is most recent from 2023, this is work done by Yiwen Chin in Zurich. So this is a different system. So here, so this is again creating these cat states where this displacement in the strain of a crystal, so displacement in now we have not just a single body, it's essentially displacement via the sort of phonon modes in a crystal, and that's entangled then with a transmon qubit via the electric field. So there's strain in this crystal, which you can then couple via the electric field to this transmon qubit. And so this is equivalent to, in some sense, a photonic mode, but in this case it's a phonon mode with actually very similar dimensions in terms of this crystal. And then this then is somewhat like the two-level system that I was discussing with the iron. And so that, the idea here is to generate entanglement between these two. So this is an interesting system in that So the mass is large, right? So this is 16 micrograms. But of course, the separation in the cat state is on the order of 10 to the minus 18 meters, which is larger than the fluctuations in the system. But so the question is, how is this? It's a big mass, but it's a small separation. So what is done in this particular case is, essentially you can, if we go back to here, if you, there's a coupling between these two, and so essentially if you, you get a cycling essentially between the qubit coupled via this piezo to the phonon mode. And what you can do then is, so if you start out in essentially a particular excited state, for example, of the qubit, then that collapses, and then you essentially get your cat state created here, and then you get a revival, and you can see this in the interference pattern in these particular experiments. And so they can do a Wigner-type tomography of this system to work out what they have created, and you can see, so this is the sort of Wigner phase space which shows regions of negativity, which of course indicates that you have this very nice cat state. And if you look at, then you can look at essentially how this negativity decays, and they can measure this, that's on, so coherence times on the order of 10 microseconds. And so with Hornberger and Yuan Chu's group, they basically calculated macroscopicity of this system of about 11.3. So much less, actually, because this macroscopicity scales as the log, it's a much less macroscopic system than the experiments of Marcus Arndt. So now what I want to do then is, so I kind of said, very early on that it's predicted that nanosphere interference, so these much larger particles, now I'm talking about particles on the order of 10 to the minus 18 kilograms, so not micrograms, but 10 to the minus 18 kilograms, but with larger superposition, seem attractive for extending this macroscopicity of these systems. And so this is, so this is my area of research. So this is, I can talk a little bit more detail in that and explain that a little bit more. So, so these are systems that, this is an optical tweezers in a sense. So this is an optical field that's focused tightly. And so this creates an optical, via the dipole force, an optical 3D potential. And these things can be cooled, and I'll talk about that, and trapped in vacuum. So they're much like an atomic ion system, so they're separated essentially or isolated from the environment in many ways, except they're not isolated from the photons, which of course is eventually the major source of decoherence in these systems. And I'll talk a little bit about that. But of course, we can have all sorts of shapes here. Usually a sphere, but you can also have these other shapes, and then you can start thinking of these things as also molecules, which have an additional degree of freedom that you can start looking at then at the macroscopic nature of that motion. So as I said, so just Thomas with the promise of this macroscopicity of 20 in this form. So in 2020, this became what I would say a new quantum system, kind of quantum, in that this system can be cooled to the ground state, and in exactly the same way, or very much the same physics that's involved to create sideband resolved cooling. And in fact, this is sideband resolved cooling. But here, this is achieved by essentially trapping. I showed you the trapping of this object within this cavity. And now there's scattering. So these are large optics. There's a lot of scattering. And that scattering, much of that scattering can be collected by a cavity. So now if I choose a cavity, essentially, that allows blue shifted light to escape. So this is moving backwards and forwards as a Doppler shift. You would expect that there's a shift up and shift down in frequency. And if you can engineer a way, which you can with the cavity, such that you can allow the blue shifted light to escape, and then you can do the same thing. You can basically take this down these vibrational ladder that exists in this potential where you're confining this particle. And so, here now we can get ground state spreads on the order of 10 picometers. And just to put that in context, these particles now have velocities in the micrometer per second range. So what can you do? What can you start to think? How can you start to test superposition in these systems? And so this is a paper by actually Hendrik and Klaus and Stefan and James Bateman, who's also working in this area. So, maybe you can just essentially take your particle that you've now cooled, and it doesn't have to be particularly cold. You can drop that again through what's here a diffraction grating, or in this case again light, because you can't make a diffraction grating small enough such that you would eventually block these particles. And then, of course, you can look at this near-field interference in the same way that Marcus Arndt has been doing this. And then if you drop these particles, you might need 10,000 of them, of the same size, you can drop them, and then you can record this pattern essentially on a plate where these particles have landed. So you basically measure that interference pattern. So that's one way of going about it. But there are other ways, and so this is work by Nikolai Kiesel, Marcus Gaspelmayer. And so we're now entered the region of promise. Okay, so these are experiments that have not yet been done. But I should say that many people now, many groups around the world are working very intensely on this process, particularly the groups of Marcus Arndt and also Nikolai Kiesel, but also Lukas Novotny in ETH in Zurich, as well as, there are others in the US and people, in the UK as well, like myself. So this is a different experiment, but it's actually, it's similar in many ways. So this is attractive protocol because essentially, as you increase in size, in complexity, these particles, for example, are not identical. If you have an atomic system, God has given you all of these particles that are the same size, but we don't have that luxury. So any of these protocols, ideally, will essentially use the particle over and over again. And unlike atomic systems where you can't trap a single particle for that long, these particles you can trap for months, or as long as the power doesn't get turned off. And in London, that seems to happen more than you would think it would in London. But so it's interesting because you can use a single particle. And then the other problem with these things is that you have limited time to do something because of the coherence, or decoherence more specifically. And not so much collisions with surrounding gas, but the fact is that you're scattering photons that lead to recoil, and that essentially leads to motional decoherence, where you then essentially you're then limited by on the order of 100 microseconds to at most a millisecond. And so everything has to be done on that time scale. So the nice thing about using this particle is there's no time of flight. And now with cooling, we have this small ground state spread. But it's still not small enough to easily do interferometry. So what you need to do is actually to trap these particles, and then you need to allow the sort of wave packet to expand by essentially turning off the field and allow the wave packet to expand. And then actually you need to use a field to even enhance that process, which is shown here. So this is accelerating that, and then you can essentially end up with basically you get a superposition in momentum, and then you need to transfer that using another potential, optical potential. So these are all optical potentials to read out in position space. So essentially you can then just go back to here, measure the position and do it again and keep on doing this experiment until you map out essentially this probability distribution from this position of this interference pattern that you get. Okay. So, okay, I'm going slower than I thought it would, but that's probably a good thing. So you can also do experiments much in the same way that the experiments of Dave Wineland with the atomic ions. You can do the same thing with embedded atomic systems within these larger particles. And yesterday we heard all about NV- centers for carrying out a range of things. But these are very beautiful systems with long coherence times, as we heard about yesterday, long spin coherence times. So you can consider that you can have a Stern-Gerlach type experiment here, where you have your particle trapped in a harmonic trap. Okay, and in this case, it doesn't need to be an optical potential. It could be a magnetic potential or electric potential. And essentially, you have a gradient, a very large gradient in the magnetic field, and you can do essentially a Stern-Gerlach experiment. So you can transfer essentially, this superposition. So if you create this, in this case, a superposition of plus and minus 1 in internal state, then you can transfer that essentially to the center of mass motion to create these cat states. And these are sort of oscillating backwards and forwards exactly in the same way that Dave Wineland had worked out for atomic ions. And you might need to then extend this by turning off the field, but the principle is the same here. So this is tricky and challenging. And there are other ways of doing that, what I won't go into, but you can also associate using other fields, optical fields, and an atomic system. So have a true atomic system which is well controlled with even lower decoherence that you can couple. And this is something that my group has been working on over the few years. So I should just briefly mention that there's also interest in actually doing these experiments in space, and Hendrik may talk about that in that essentially you have much longer time in space to carry out these experiments because you will need a lot more time, and so there's a significant interest of doing that, and I won't go into that much further. But what I did want to talk about briefly is so this is a really a proposal led by Shugato Bose, who has looked at these systems and to really see, well, they're in an interesting regime, right, where they're much more massive than atomic systems, and so they're susceptible to gravitational interactions much more. But they're small enough that you can treat the physics a bit like an atomic system. And so so let me just quickly, I showed you this experiment here, which is essentially a Stern-Gerlach type experiment. Okay, so this is basically a Ramsey interferometry experiment. Now, if you can do that, which we can't yet do, but I should say again, there are about 5 groups around the world who are working on this particular experiment. And the reason is that it shows promise in terms of telling us something about gravity and the quantumness of gravity. And so the idea here is you have essentially 2 superpositions. So if you can create 1, you can probably create 2. Getting that first one is tricky though. And the idea here is that you create 2 interferometers. So this is 2 Ramsey interferometers using this technique that I'm talking about. But then you have entanglement between the 2. And that if this, so the idea is if you get entanglement, that means this gravitational interaction is a quantum interaction, quantum entity. And so really that's all it tells you, but it's a lab experiment that can start looking at the sort of quantumness of gravity. And so this has sort of garnered a lot of interest, but there are many complications with that, and I can talk about them if I want. So I must have almost more or less run out of time, right? Yeah, okay. I had quite a few things, but I mean, you can ask me questions. So what are the requirements for these things? So because of the timescales involved, where you need to make a measurement, that you need ultra-high vacuum, you need low environmental temperatures, but eventually you need low internal temperatures, and these are all difficult things to achieve. So we need to cool and control all motional degrees of freedom, and had I time, I would have showed you that. And we need to reduce this back action from recoil, and you need a detailed understanding of these systems, which is often what you need to do is you need to trap one of these systems and actually do a lot of characterization before you can even use it, before someone turns off the power. Okay, well, I was going to talk about a few more things, but I'll just sort of finish off with this last one here before I conclude. So this is another interesting type of experiment, and because these can be considered, if they have some shape to them, they can be considered to be a molecular system. Then you can apply the toolbox of molecular physics. And so this is a particularly interesting experiment where essentially if you have a rod like this that you can cool and align, that in terms of rotational motion represents a superposition of rotational states. And then if I was to turn off this confining potential, so this aligned state is the superposition of many rotational states. If I turn it off, then they start evolving. So the wave packets start to spread. And what you see as a function of time is that you get revivals in this alignment process. And this is type of interferometry on equally massive particles. And so the idea is that you cool, you prepare this, you align it, you allow it to evolve and make a measurement, and you should get a revival in the orientation of this particular particle. And so it's an attractive experiment, but if you look at the time scales, they're quite long in terms of milliseconds, which makes it a little bit challenging. But let me, I was going to go into a few other things, as you can see. But let me finish off. I think at least I've reviewed many people's work and a little bit of my own, so I think that's quite good. Obviously there's so much work that it's hard to really, provide a proper overview. But I've given my personal perspective of what I think are probably the most important experimental progress towards really creating a large macroscopic systems. And hopefully I've talked a little bit about what are the limitations and what you have to overcome to do these experiments, and they're quite significant. And it's why essentially the first paper on on these levitated systems, it took 10 years really to get to the point where you could actually at least prepare a state so it's ready for superposition. So in the next 5 years I expect that you should see a lot more. There's many more groups working on this. So I've just sort of given a personal view on these levitated mechanical systems, which I think are a leading platform for really pushing this into much larger mass regimes. So thanks for your attention.
So we'll have a question and answer plus discussion section after the coffee break, so you can ask all your questions. And some of the things that you missed showing here, you can show over there.
Okay, thanks.
Right.
You're up next.
Mike.
So our next speaker is Professor Hendrik Ulbricht. And to give a bit of background, Professor Ulbricht did his PhD in the year 2003 from Fritz Haber Institute in Berlin. And following which, he was a postdoc at Vanderbilt University in Nashville, Tennessee. And after that, he was in University of Vienna. And he joined the faculty of University of Southampton in the year 2008. And his research interest concerned experimental test of fundamental theories of nature by tabletop experiments, but also in space, as Professor Barker mentioned. Some tests are concerned with the large mass limit of quantum superposition principles, which forms the basis of quantum mechanics. Other experiments are concerned with testing the interplay between quantum mechanics and gravitation in the low energy limit. He also performs quantum experimental research on preparation and analysis of massive systems in non-classical states by various techniques. So without further ado, I would hand it over to Professor.
Okay, thank you very much for this kind introduction. Thanks for having me. It's great to be here. Great to see you. Lots of old friends. Hopefully new ones very soon, adding to the family. So I talk about these quantum to classical transition in massive systems, so macroscopic systems. And Peter basically has said all the important things already. I just illustrate some aspects and give you also some maybe background on some of the ideas, conceptual theory ideas, which we want to test. And I hope it's enjoyable, and I also have many slides, so I don't have the ambition to talk about everything, but let's see how far we can push it. So the first thing I want to say, just to get it out of the way and to make sure that I have done this, is to thank basically the people who are involved in the research. So at the top is people in Southampton in my research group. So we are experimentalists as well. Mainly we do experiments. And that's over the years, all these talented young people. And then there's a lot of collaboration on foundations. So TP is here and Deepanka is here. And so we work on concepts and collapse models. I talk about collapse models a little bit. And then, of course, also how gravity may play a role in this quantum to classical transition. There's funding, and then there are like networks where we try to steer a little bit how science goes, and also funding maybe comes in certain ways. So maybe let me introduce and put this a little bit into context in general, with quantum systems. So Peter talked about this macroscopicity value, and of course you can say, and you can ask these questions: what is like a macroscopic quantum system? Yeah? And you can say, of course, it could be simply size. So if one of the fantastic experiments by Nicolas Chisin or Harald Weinfurtner, who's also somewhere here, I think, you have entangled photons and you separate them by like kilometers or something like that. That is, truly macroscopic, of course. So what we are mainly interested in is like a different type of macroscopic, which also includes the mass of the system. Yeah? So we have this requirement, and that is why this macroscopicity value, which Peter showed you, is a bit more complicated. Is it involves the size of the quantum system. So if you think about a superposition experiment, like in a double-slit experiment, what is like the distance between the left and the right-hand side, so that is the size of your state. But you're also interested in including the mass. Yeah? So you have a single particle which you put in the superposition. What is the mass of the system? So if the mass is large, then that contributes a lot to macroscopicity, and then it also is more macroscopic if you can keep the superposition for a long time. So there are 3 parameters which you include this, but of course, there's Harald. Yeah. So there are these 3 parameters, which is a set of system features which you want to test this specific type of quantum to classical transition. Yeah? And the idea is, of course, that Peter mentioned it already. You have a system which at the same time is very massive. Yeah, so much more massive than an atom. So you have these nanoparticles which have, I don't know, 10 to the 15 10 to the minus 15 kilograms. So that's like, many atoms which are sitting there together. And you look at the center of mass motion of this, composite object, if you want. Yeah? And now you want to basically keep quantum features of the center of mass motion. Yeah? You want to put it in a spatial superposition, for instance, or you want to prepare, quantum states of this center of mass motion. And at the same time, it is so massive that gravity starts to play a role. So gravity effects may mix in, and there is a whole bunch of different ideas how gravity can now affect the dynamics of such a massive quantum system. And that's the regime where we're interested in, and we try to push experiments to explore this. So that is maybe like an introductory remark, and I will talk, as I said, about the theoretical ideas and then also talk about these large mass systems. Just to give you a heads up on the type of experiments is very similar to what Peter talked about, levitated optomechanics. So you basically have a particle, typically silica, which you trap by light. And then as in all optomechanical systems, so you may be more familiar with these cantilever and cavity systems. So there's an optomechanical coupling, which means that if you think of a cavity, and now the cavity has one mirror which can move, then you can think of that if there's this motion of this one mirror, it has an effect on your cavity mode. So the light in your cavity is affected by this motion, but at the same time, there's like a light pressure effect of the light on the motion of the particle. So the light is pushing basically this movable mirror, and is therefore also affecting it. That is light matter coupling, and that over the past decade or so could be pushed deep into the quantum regime, so you can basically use light to prepare non-classical states of this mechanical oscillator, which is one cavity mirror. So that's like the prototypical optomechanical system, and this levitated version is a very specific one where you have the advantage that now the particle which you trap, the center of mass motion of this particle, is your system which you control. It's an harmonic oscillator, continuous variable, but it is highly isolated from the environment. So you don't have any kind of substrate which connects it to the outside world. It is just coupled, if you want, by the trapping field. Is a very, very soft spring, and that makes it an isolated system. And for quantum experiments, that's very promising because decoherence is, of course, the biggest issue in all of this. So that is one type of experiments where I will give you some examples how to push into the quantum regime. Here's a second type, which is also a levitation experiment. So the red dot is a permanent magnet, a ferromagnet, and that's levitated in the cryostat by superconductivity, so by the Meissner effect. So the gray box is lead, and if you cool lead to below 10 Kelvin, it makes a transition into a type 1 superconductor, as I guess most of you know. And then by the Meissner effect, which is one of the features of a superconductor, is ideal diamagnetism, so it repels an external magnetic field fully. So it generates basically an opposing magnetic field which has the same magnitude. And that means that you have here, your magnet has a permanent magnetic moment, so that's a dipole, if you want, that generates an image dipole, and that is repelling and levitating the particle. And you can shape the lead to make it really a 3D stable trap. And that is a very nice system. Again, it's levitated, it's decoupled from the environment, it's completely passive. So in the optical trapping experiment, you still had the laser, which was used to levitate the particle and also to manipulate the center of mass motion. But the problem there is that, of course, you have noise in the laser, and that is always mapped somehow onto the center of mass motion. In this case, it's completely passive, and you don't have these issues. Okay, so they're different levitation systems, and they have advantages and disadvantages. This passive system is very nice for a low noise experiment where you want to have a very sensitive detection, if you want, for gravity, for instance, and I will, if I have the time, talk about it. But the disadvantage is that it is really hard to access and engineer the center of mass motion, so to control it, because there's, to start with no field which you can modulate. While in the optical levitation case, you have optics, you have the light which you use for trapping, and in light we know so many things which we can do to manipulate and to generate states, and that you can map on the motion of the particle. So you have this engineering capability, but at the same time, as I mentioned already, you have also noise and decoherence effects which you couple to the center of mass motion. So you have to think about what is like the best system for whatever you want to do. Okay, that was just a precursor. I already realized that I talked much more than I wanted on each slide. Let's go to like the theory, ideas, the models, and to test. And the first one, of course, is collapse models. So there's this paper which we wrote with TP a decade ago, which is now cited a lot and had, I think, a very good impact. What we did there is we basically summarized the specific type of models which want to explain, in a way, the quantum to classical transition. So, of course, the idea is that, initially everything starts with a quantum system, and then something happens, at least, in some views or some interpretations, which then, changes the dynamics from a quantum one into a classical one. And the question is how to describe this. There's, of course, decoherence, which is like the leading argument how that may happen. So it's an effect of the environment which is somehow measuring your system, is localizing your system, if you want. And these collapse models have a slightly different philosophy, so they don't want to push basically this mechanism to the environment. They want to keep it as part of the dynamics. So here's an equation which I will not explain into full details, and I always say this, if you have questions, please ask TP. But here you are. So that is, Schrödinger equation, and you know, like the first term on the right-hand side, and the other stuff is basically all the tools and the ingredients you need to make these collapse models consistent. Yeah? So there are some issues which come up if you want to come up with a dynamical equation which now describes initially a quantum system. So there's Schrödinger evolution, which is linear, but it also wants to describe how this linearity, the linear evolution, is broken. You have the collapse of the wave function. You break unitary evolution, and that has to come from some sort of nonlinearity. So as we have learned from, amongst others, Nicola's work, is that if you blindly put a nonlinearity in the Schrödinger equation, then you run into problems. You allow for faster than light signaling, so that's not consistent with special relativity, so with covariant formulations or with Lorentz transformations. So that is therefore rejected very often. Let me have a little bit of water. So there's a trick here, which these collapse models do to avoid this problem, and that is to use a random field, a stochasticity. Yeah? And that is this omega term. So omega t is a stochastic field, a classical stochastic field, which is now playing the role, if you want, of the observer. And in this models is not defined by any physics. It's just a mathematical model, which now, in a way, you can think of this. You have your quantum system, which is basically probed by this random field. So there are basically kicks, position measurements in this specific model, which are, if this effect is strong enough, collapsing the wave function or localizing your system, and then it becomes classical. And all this dynamics is described in the same equation. It's all contained. And this capital M is a mass operator. So this is the so-called CSL model, and that is mass dependent. So the idea is that if you have a small mass system, a microscopic system, then it remains quantum mechanically. You can have superpositions, and you can do all of the stuff you want to do in a quantum domain. But if you increase the size, if you increase the mass of the system, or if you want the macroscopicity, then this collapse happens, and this noise field starts to act, and it basically collapses the wave function, and you go over into the classical dynamics. Okay, that's the idea. What I like most about these models is that they're actually testable, so they have a clearly distinct prediction if you compare basically to standard quantum mechanics. So you can, set up an experimental setting where quantum mechanics predicts a completely different outcome compared to this model. So pure quantum mechanics would predict you can always generate a superposition, you can always maintain the quantum state as long as you can shield from the environment. While these models say, no, there is like a fundamental threshold, and it's impossible universally to have quantum systems which are more macroscopic than this threshold. Yeah? So it's, in that sense, fundamental. And I think maybe let's leave it there. We can discuss more if you're interested. What is really interesting is these things here. So if you take this more serious and you not just use it as a toy to push your experiments into macroscopicity, then they predict that there should be, and that's now the physics, they predict there should be a universal noise field, a classical noise field, which is filling the universe and is acting on every system. Yeah? And you may think, okay, that's strange. That's a strange idea. It's somehow something like the ether, which we know from Einstein and from special relativity. That doesn't seem to be the case. That there is something like that. If you then think about dark matter, maybe even the Higgs model, or cosmic microwave background radiation, gravitational waves, then you realize that maybe, or even quantum vacuum, so there may be some stochastic effects which we already know, which could have this kind of effect on a quantum system. Yeah? And I think what is a really interesting exercise, and some people have started to do this, is to go through this known noises, if you want, in the universe and try to map them to this dynamics and see if they can generate an effect which is in agreement with what we see. Okay, very pragmatically, these models come with two parameters. So there's a collapse strength, gamma, RC, the localization length, and lambda is the collapse rate. So again, that is very similar to what you may know from decoherence, from open quantum system dynamics. You have this noise, and the way the noise, you characterize the noise is by the rate, so how much of these kicks, how many of these kicks you have per unit time, and the localization length, so that is basically the correlation length in the noise, which is the other parameter. So that, is in a way the ability of the noise to localize your system. So that maps really nicely to intuitively to decoherence ideas as well. And then maybe let me explain this briefly. So the prototypical experiment to probe experimentally these collapse effects is of course to do interferometry. So you generate a superposition of a more and more massive object. So you increase the mass in, if you want atom interferometry, you go to molecules. We have heard about these beautiful experiments by Markus Arndt, and then you try to push to nanoparticles, and then at some point it should become impossible to do it. Yeah? So now there are other ways. That is like, as we all learn, a very complicated and difficult experiment. So we thought maybe there's a different way, and the different way is to do what we call non-interferometric tests. So you don't generate a superposition at all. You just look directly at the noise, which is predicted by these collapse models. And you can, again, do it with any system which is sensitive. And one of the most sensitives, again, are these optomechanical systems. And the schematics basically shows, again, there's this cavity, and one of the mirrors is movable. I think this is the pointer. Yeah, so this is the movable mirror. And the movable mirror is now affected by, all sorts of noises, and there's one of the noises could be, the collapse noise, and that would basically do some sort of Brownian motion of your mechanical oscillator. And now we have a very big mass, so it should be very sensitive to look at this, and that's indeed a way where we performed experiments, and we could set bounds on these collapse models. So there's a review if you're interested on especially these non-interferometric tests, and what it basically boils down to is an exclusion plot. So if you know particle physics, dark matter models, so the thing you always have to show is exclusion plots. So you have to show this is what the model predicts, and in the same plot, that's what the experiment has excluded. So that's this plot. So here's lambda and RC, so the two parameters of the collapse model. So that's again for CSL, continuous spontaneous localization. And the colored regions are excluded by experiment. So the green one, for instance, is looking at Brownian motion in a mechanical system. So that's experiments which we did with Andrea Vinante some years ago. The blue ones are gravitational wave detectors. So you can actually look at existing data from LIGO and also LISA Pathfinder, wherever they have big masses which they control well, and they understand the noises in these systems. You can use the existing data and can put bounds on these models. So these are on the right-hand side, the blue, and then you have these orange things, which is mainly from X-ray emission in germanium. So that's another effect which is predicted by these collapse models, is that you should have spontaneous emission because you have acceleration of electrons in these crystals by the noise, and accelerated charges emit radiation, and that is the effect which you can predict and calculate. And because you don't see it, you can exclude that collapse models exist in this region. So you see the still remaining region is this here. It's still many orders of magnitude. That's the original proposal by Girardi, Rimini, and Weber, which maybe some of you know. And what we have excluded already are two models which were put forward by Stephen Adler. Yes, so it's getting closer. The experiments also there, non-interferometric, getting harder, but we are still working on it and pushing for it. And I, will show you some of the things we are doing. I think this is, all I want to say about collapse models. Again, maybe let me emphasize that these models as such don't include physics, so they don't actually say what is the noise field. That is still an open question. They use white noise, which is in a way unphysical. So you would basically expect that any kind of real physical effect would come with a clear frequency, or like a frequency fingerprint, so-called colored noise. And I think that is like the thing which one should try to do, is to take a piece of physics, turn it into a certain frequency characteristic, and then see if this sort of noise is doing the trick in these collapse models. Gravity, because that was like one of the things I wanted to talk about, is of course what we in a way suspect and would like the physics to be in these collapse models. And there's of course the Dioggi model, which is doing this in a formal way already. And they can also be tested. I don't talk about this. There's Penrose's idea, which is related. It does not include the noise. They're sometimes called the Dioggi-Penrose model, but in reality, if you talk to the two gentlemen independently, then they think we have completely different ideas and they're not even related. But again, in a way, also in Penrose's model, the idea is you do like a macroscopic quantum experiment and you want to see that there's an effect of gravity kicking in. And he predicts a certain threshold where that should happen. Okay, so yes, so let me maybe go in this one. There's also, now I want to talk a little bit about these gravity ideas in the context of quantum mechanics. So I already mentioned the Dioggi and the Penrose things, and there's more. And in general, I guess these two cartoons show the approach or the thinking. Yeah? So it is actually about gravity, and to test gravity with these large mass systems. Again, levitated systems are, I think, the most promising one. Peter talked about this entanglement idea, and the question there is if you can use these experiments to actually probe if gravity is quantum, in the sense that it can entangle two masses. Yeah? So you want to probe if gravity has a feature which allows you to do the entanglement. The other idea, which is happen to exist in the same kind of parameter regime, is this one. Now you go back to a quantum superposition experiment. You take single particle, you put it through your double slit experiment, and you do this with a large mass. And the question is, how does actually the gravitational field of such a state look like? Yeah? So this experiment has never been done, and it was discussed in this very famous Chapel Hill conference, Feynman, and the original idea, I guess, is from Bronstein. So the question is really, if you do a superposition of a single mass, you put it into locations, if you want this language, then the question is, how does the gravitational field, or how does the space-time of such a state look like? Is it also in a superposition? Is space-time able to be put in a superposition or not? Yeah? And again, what you want to learn is if gravity is fundamentally, quantum mechanical, or if it is different. Yeah? I mean, we know already that it is very different. Not even the force, space-time curvature, and all of these things. And now the question is there like a quantum aspect in it? Yeah? And what could it be? And you know that there's this very big question behind. And people try to quantize gravity for ages. They're looking for the graviton, but that is like in a high energy regime. So what we want to do is to go in a low energy regime. So here's like an overview, which I always show for this. So what you see here is a mass scale. Yeah, so that is small mass here on the left-hand side. That's the domain where quantum mechanics exists. So atoms and small molecules, electrons. And then here's the large mass side. So that is like kilograms. You have LIGO mirrors and really macroscopic systems. This is where gravity lives. And now the question is, what happens in this intermediate regime? Yeah, so again, I told you what we want to do is we want to take these quantum systems, generate, for instance, superpositions, and push the mass up and see what happens. And in green, I have indicated what are these different proposals, models, theories, which are there, which would be tested in this regime. And at the same time, not necessarily with the same experiment, we want to take masses in this gravity experiment. So two mass gravity experiments. One is the source mass, one is the probe mass, and we want to push the mass down in gravity and actually find out in experiments what happens if the source mass is very small. Is still, Newtonian gravity as a first approximation correct, or is GR still describing what's happening, or is there something new happening if you, for instance, go to Planck mass, which is 26 micrograms or so. Yeah? So these are the ideas, and that is what we call the low energy regime. Yeah? So we're not looking for the graviton. We don't want to build an accelerator which is as large as the Earth. We actually want to take a quantum system, increase the mass so that we see how gravity affects the evolution, the dynamics. Good. So how do we do this? I think I have some models still. So what's the time?
So you can go up to like 10 past 12 because you started a bit late.
Okay, so that's like 20, 25 minutes, 24 minutes. Okay, so let me do like a quick tour through these gravity ideas before we go to the experiments. So here is this Schrödinger-Newton equation, semi-classical gravity, a much hated model, predicted and worked on early by Möller and Rosenfeld. And the idea is you take Einstein's equation, the first line, and on the right-hand side in the energy momentum tensor, you put in something quantum mechanically, expectation values, and then you just, try to solve it. You're a good mathematician, and you can actually, show, you can translate it down to something like of the Schrödinger equation, and then you find in the Schrödinger equation here in the first line that you have this extra two terms. So that is basically gravity interaction with an external mass. That's not so interesting. That's what they do in atom interferometry. And then here there is this self-gravity. That is this idea that you generate a superposition that actually now, because gravity is maybe different, it is semi-classical or classical, then it is not in a superposition. So that means there's still some mass in both of these parts of the superposition. So there could be a gravitational attraction between these. So, you're really pushing it there. So that's highly unconventional, and you get crossed with many of the beloved principles, especially in, in quantum field theories, which are, super successful, of course. But, you have this effect, and again, you can write it out, and that is basically the self-gravity, and you can estimate, if I wanted to do an experiment to test the self-gravity, where do I have to go? And that, I think, is on the next slide. So you see there's a mass and a time, and the red region, the red box, is where you have to go to test the Schrödinger-Newton equation. So the idea is very simple. So what you say is, okay, I do interferometry, I do the double-slit experiment, I take my mass, I split basically the beam, and I recombine. And now if I do this, what the Schrödinger-Newton effect should do is it should basically contract the superposition state. So if I don't do the recombination, if I just split these two wave packets and they propagate, then Schrödinger evolution tells me that it disperses out. Yeah? If I turn on this Vg, the self-gravity effect, then it means that there should be a contraction. Yeah? So basically the wave packets or the wave function is coming back together again. Yeah? Okay, so if you put in numbers, you find that you need super large masses, and you need, so the Marcus Arndt is here somewhere, so they push to 10 to the 6. I think that's like the unofficial record now with sodium clusters. So, if you want to go to the red box, you have to increase this by orders of magnitude, and also you need like 100 seconds of free evolution time, so you need to give this time to the wave function to expand and then show that there is some contraction. So that is nothing you can do on Earth, so that is, a satellite experiment where you have these long free evolution times. And maybe at some point there's a chance to do that. You can also do that other ideas. So the Caltech group, they came up with a specific feature in squeezing, which should be, if you want, Schrödinger-Newton phase in the evolution of an harmonic oscillator optomechanical system. So we came up together with André Grossart with this idea that if you have a quantum mechanical harmonic oscillator, then the Schrödinger-Newton effect should do what all effects do to the harmonic oscillator. There's a shift of the energy levels, and also like an, a displacement and a shift. Yeah? So you can, if you could do spectroscopy, if you could measure the energy of states of an, quantized harmonic oscillator of a very heavy mechanical system, so you take optomechanics, cool it to the ground state and excite into, the higher states, and then you measure basically what the transition is, then you should see a shift because of the Schrödinger-Newton effect. Okay, maybe that's the last thing on theory. Here is, some more details on this Feynman/Bronstein question. How does the gravity of a superposition actually look like? And there, again, that's like the approach which we're taking is we try to come up with cases where, quantum mechanics and classical mechanics predict different outcomes. So here's, the quantum outcome. So I should maybe say there is like two masses in the system, and what is shown here is only, actually no, there are two masses. So the classical case is maybe interesting. So this is like the superposition case. So that would be your source mass, and then what is called S2 is the probe mass. And because, again, in semi-classical, you don't have a superposition, so you basically have this coexistence of a little bit of mass here and a little bit of mass there. If you then have your probe system and you shoot it through, this kind of situation, then what you should see is like a, if you want, probability of your measurement outcome is you measure that your probe particle is in the center of your setup. Yeah? So now that is the classical case. In the quantum mechanical case, you have the same situation, but now you allow that actually space-time also goes in a superposition. So you have two cases, and these will be, as always in these quantum experiments, the random outcomes of your experiment. So you will first have, in a way, you have the superposition, you collapse the gravity part in the left-hand side, and then your probe system will go towards this because that's where the mass is, plus the option that actually gravity goes on the right-hand side, and then your mass goes into the opposite system. So if you run this experiment many, many times, then the average, the ensemble outcome would look like this. So like an interferometry experiment, so it would be a clearly different signature of your experiment. And that is the idea, to push basically to the regime that you have these parameters, you have sufficient mass, you can initially prepare at least one of these systems, the source system, in a superposition, and then you see if you get this result or this result in the experiment. Okay, I skipped this. There's also, Peter mentioned rotation, so you can also do this superposition not in a linear way, you can also do it in an angular way, so you can use non-spherical particles, for instance, and you can put them in a superposition of different orientations, and then there are the numbers in a proposal type of exercise in a feasibility study if you want, where you could probe this. And also there, as always in these experiments, the critical issue is this free evolution which you need. So what you do is you prepare your quantum state, and then you have to let it go for some time, and then you probe how it basically evolved. And that time for the free evolution, after you have prepared the state, that becomes longer and longer if the mass gets larger and larger in the system. And that is like the critical part, I think, in my view, of this experiment. Yeah? So to allow for sufficient free evolution time. All the other things are more or less solvable in technical terms. So that's now the very last thing, and then I switched to experiments for the last 15 minutes. Peter talked about it. That's Sugato's proposal, very similar one from Chiara Maletto and Vlatko Fedral. You have these two particles, you put both in a superposition, you allow gravity interaction between the two inner parts of the two superpositions. If gravity is able to entangle these two masses, then when you recombine, you should see typical correlation, like in, for instance, Bell experiments or so, in the outcomes of the two interferometer measurements. There's a way to explain this, which I like a lot. It goes back to Mauro Padernostro and Tomek Paterek. which is more like a quantum information way to explain it. So in this case, you have two systems, A and B, and you have C, which is an interaction which you can turn on and off. And now you do the following exercise. You have first C is interacting with A, and then shortly after C is interacting with B. And now the question is, what is the condition on C so that this protocol can be used to entangle A and B? And the answer is you need some sort of coherence in C. Yeah? So you need to be a quantum entity of some sort, and then you can entangle. And now in the case, and that's a very general kind of approach and idea, and you can replace C with whatever you want. In the case of Sugato's proposal, C would be gravity. And the question is exactly this: if gravity is a quantum entity and can actually do the entanglement. Again, you see in this box here the numbers, and they're like really super challenging. So this is a large mass. This is a super large superposition size. If you bring these two particles, close together, so you have to do it because, gravity is super weak, as we know. And then there are, different interactions which are typically stronger. Everything electromagnetic, everything which has to do with charges, everything which has to do with dipole moments, electric dipole moments, everything which has to do with dispersion. So like van der Waals or Casimir-Polder interaction is much, much stronger than gravity. So you have to do something, you have to screen, and that is where the difficulty of this proposal actually is. But as Peter said, there are now around 5 groups in the world working on this specific proposal and to do this Stern-Gerlach type of experiment. Good, I think with this now I should mention Dipankara's, the work we do with Dipankar and also with Sugato. They're always, and that's actually something I find really fascinating. There are many ways if you think about these problems. So how can you actually investigate gravity? How can you learn if gravity is quantum to some extent and do like an experiment to probe really into it and to get some indication of how it could be quantum. Yeah? So here's an idea that you actually use the measurement. And as we know, measurement in quantum mechanics is very different from measurement in classical mechanics. So in quantum mechanics, the measurement has a big effect on the state which you get. Lots of discussions around it. So now if we could apply this to gravity, so if we basically could generate a situation where we have a gravitational interaction and now we probe, we measure this gravity, and if gravity is a quantum entity, then it should behave like a quantum object, and this measurement should have a strong effect on the outcome, basically, of this measurement. If it's classical, then it should not. And that is a proposal which puts this into an example and works out how you could do it. And that, I find it really interesting to think about this. It's really, in a way, taking the things we know from quantum optics and applying them to gravity situations and see how, what we learned about light, what we learned about photons by doing non-classical experiments. How can we map those to situations with large masses and with gravity? Good, okay, now the experiments. So here is a concrete proposal to do superposition. Peter talked about, many others. This is one which is basically taking these ideas from molecular interferometry. So you do like a Talbot interferometer, a very classic type of interferometer. So you have, if you look at the left-hand side here, so there's like your source, which is the particle in a trap, and basically what you have to do is you have to somehow generate coherence, which is very interesting that you actually can do that. And you do it by cooling, so that's what everyone does in atom interferometry. So you cool your atoms because you get a coherent, spatially coherent source. And we do the same here, so we have a particle in a trap, and we cool the center of mass motion. And then when the initial state has a certain temperature, which is 1 millikelvin or so, then we turn off the trap and we pass it through a grating. So this is a light grating, a standing light wave, very similar to what you have seen in Markus Arndt's experiments, as explained by Peter. So this is where you generate a superposition. Yeah, so that's this part, and then you need, that is your free evolution time. So here you generate a superposition, then here's your detector, And you do this for one particle, and you get basically a click, or you detect your particle in a certain localized position, and then you have to repeat this many, many times. And if you're lucky, you get an interference pattern which shows this kind of typical interference pattern distribution. Yeah. Okay, so again, the most critical part of this protocol is basically this part here. So where you know, after you have applied your operation, your gate operation, if you want, you have generated your superposition state. Now you have to basically wait until it maps in position space so that you can detect this as an interference pattern. Yeah? And that goes with 1 over m. Yeah, that's like the Schrödinger evolution. So if you have a large mass, that takes like really long. And that is what is plotted here. So you have this is called the Talbot time. So that's the time from the grating to the detector. And that's the mass. And you see there's this kind of linear relation that's actually here logarithmic. So you have, you know, you need like, what is this, 10 seconds if you want to put a 10 to the 8 atomic mass units superposition in the experiment and see an interference pattern. Yeah? That's only 2 orders of magnitude larger what Marcus Arndt already has. Yeah? So very soon, these experiments will be limited by your ability to do free evolution. So now, if you think of this in a concrete setting in a lab, so this, you know, 10 seconds means that you already have 10 meters or so of a fountain, right? So that means you have to shoot your, so let's say if you do a vertical experiment, as they do in Vienna at the moment, so you start at the source, you go through the grating, and then you have 10 seconds. So in this time, particle will go on 10 meters. Yeah? That's a big experiment you have to build. So you can think about turning the experiment in a vertical position and shoot up, yeah? But then also you need at least 5 meters, so you have a factor of 2 reduction because it goes up and then it comes down. So these would be like a very bulky experiment. Yeah? And if you want to do this, you have to actually cool the initial state much more to make sure that the particle comes down at the same position and not going anywhere, yeah? So that you don't have a, you know, transverse velocity which would come from a higher temperature in your initial state. So that's super tricky. Nonetheless, so we are trying to do this. Maybe, you know, if you have questions, I can talk about it. That is how we do the trapping of these particles. We use parabolic mirrors. These are silica particles, 100 nanometer at the moment. We can trap them and we can cool the center of mass motion by optical parametric feedback. So that's a nice harmonic oscillator system. And that is the source part. That's the source of the interferometer. And now you see here's a configuration where we did a theoretical analysis. So here's the parabola. Particle is trapped, and then we would have a second laser which is kicking the particle up, and then it's coming down, and then you detect basically in the same you know, field where you initially trapped the particle. That would be the source, the detector, and the kicker would be shoveling it up to the grating, which is up here. Yeah? So that's basically the folded Talbot interferometer, which gives you this factor of 2. And we think if you ever realize this, we could actually, you know, see that is like the fringe visibility difference of classical and quantum. It's very difficult. I don't go into details, but you're basically within one Talbot range, which means that you don't have clear interference fringes anymore, but you can still see a difference between, you know, quantum and classical for some parameters. So this is here the energy which you have in the grating, and that basically defines the phase which you imprint on the motion of the particle by the grating. Yeah, that is basically the generator of these of the superposition. So we think, you know, to do small superpositions, so that means the superposition size would be smaller than the actual size of the particle. We think we could do this with something like 10 to the 10 AMU in the sub-Talbot regime. But you know, the free evolution time is this here. That's 100 milliseconds, which you get at most, yeah, with the best cooling you can do at the source. Okay, so now the next step is really to take it serious and say, okay, what would be the best environment? And that is on a satellite. So there's this macro proposal, and we have taken some steps to realize it. So there are a lot of theory papers where we study this case, and that's like a decade-long, you know, community development. But in free fall, yeah, on a satellite, if the satellite is freely falling on an orbit around Earth, or it sits in one of the Lagrange points in the solar system, then you would basically have the case that, you know, here's the protocol. So you have your initial particle which you still cool optically in this optical trap, and then you turn off the trap, and because now you're in free fall, your apparatus is actually falling with your particle, so there's no motion of the particle relative to your detector, which is of course not true because there's always acceleration, so there's always, the spacecraft is moving a little bit, but ideally, it would be fixed there, and then you apply a grating pulse, to generate the superposition, and then you wait, and then after some time, there's basically the build-up of this interference pattern, which you then would detect. Yeah? And now if you do this in space, you would basically get something like seconds or longer for the free evolution time, and that would allow you to seriously push the macroscopicity in this interference experiment. So we have taken first steps. That is actually what I wanted to show you. That's quite cool. I'm very proud of it. So within 1.5 years, we have built, that is the size of a toaster, we have built a fully autonomous optical trapping experiment. So there's, I think, more details here. So inside there's a vacuum chamber, which has an optical trap. We also do a magnetic trap, where I don't have time to talk about it. We have an electronic system, a laser driver, which is trapping the particle, and also in the second step, so not in this very first experiment, is running the protocol of an interferometry. So it's trapping a particle, cooling a particle, releasing a particle, turning on a grating, and then measuring the position. So that is basically all in this platform. There's an FPGA and so for experts, which is running this protocol. There's a microcontroller, which is turning on and off everything, and then also saving data to the satellite. So this thing we have actually built. So this is Jack, the PhD student who spent this 1.5 years of his time. So I think he feels like he has spent a decade on it. But that is like the final result. That's our payload. And we have just last week delivered this to Munich. There's this company, the exploration company, that built this launcher. So that is a capsule which in the future will transport people to Moon and Mars. And because they're not allowed to transport humans at the moment, we are basically having some space to put our experiment there. And that will be launched next June from California by SpaceX. So we will have half an hour of free fall trip. And what we want to do is we want to show that first this levitated optical levitation technology works in space, that we can trap a particle in orbit, and then prepare for a longer mission to actually do interferometry. So that is very concrete. And actually they had me to wear this coat because they didn't like my shirt, but I look very sciencey in this. So I usually not look like this. Okay, good. Now 5 minutes. Peter also talked about it. There's this other idea that if you don't want to wait for this long evolution time, if it turns out it's too difficult to do 1 second and longer, then you can actually try to expand, to boost, to accelerate the Schrödinger evolution by a certain type of operation. I can talk about it if you're interested. That's experiments which we have done, so you can do squeezing of the mechanics. So it's not using squeezed light to detect the mechanics, but you can generate this phase space of this harmonic oscillator momentum and position. You start initially with the thermal state, so that should be circular. It's not entirely, just experiments. And then if you apply a certain operation, a squeezing operation, you squeeze basically this mechanical state that's rotating in phase space and then rethermalizing. So if you use this as an interaction and you actually apply multiple of these squeezing operations in the right time sequence so that you have a constructive build-up, so you basically grow your squeeze state, you make it larger and larger, then you can use it to do all sorts of interesting things. So you can, for instance, generate bimodal states, and that is because you can access a nonlinearity which is intrinsic to this, particle in the trap. So it's not a perfect harmonic motion. So you have x to the 3, x to the 3, x to the 4 nonlinear terms for large amplitudes. And if you access them by the squeezing, you can make the dynamics to be dominated by these nonlinear effects. If you pre-cool the state, I think that's on the next slide now, you can actually, generate negativity. So now that's the Wigner function, and you see there's negative parts in the fringe. So the idea is to use this nonlinearity as another form of beam splitting to generate the superposition state. Slightly different protocol. What fits better to the main story of my talk is actually you can use this to boost, to expand the state. Yeah. So a critical thing for all of these protocols for generating superpositions, but also the gravity thing, is that you need to engineer basically your state, and you need a coherent state to some extent, and that means that you cool. So your initial state is pretty small. So you see this is in nanometers, so that is so the diameter is maybe 0.5 nanometers, so 5 angstroms. Yeah, that's the size of your motional state. Again, position, momentum, and phase space, yeah, momentum, position. And now if you apply for 1 millisecond, many of these squeezing pulses, you can actually expand the state to something like, that goes from, let's say, plus minus 100 or so that is 200 nanometer size. So you basically boost the size of your wave function, yeah. So we still have to demonstrate that this is actually a coherent operation, but now you have a big state and you have many more options to apply a grating or apply another, beam splitter protocol, because that's another critical point, is that whatever you want to use to split basically this wave function, it has to have a smaller structural size than your wave function, right? So, and if you can boost it, if you can make it large, then you can win. Okay, so that maybe just to give you some flavors of things we can do. I think I'm out of time. This is like how it would look like in this plot. So if we manage to do this nanoparticle interferometry, we would actually move to this part in the overview plot. Now I didn't mention the gravity stuff. Maybe just one slide. We did the gravity experiment. That is with this magnetic levitation in the cryostat. That's a dilution refrigerator. And there's an external mass of 2.5 kilograms, which is modulated. That's on a bicycle wheel. Yeah, that's the source mass. And then the levitated particle in the box. In this case, it looks a bit, it's not a spherical particle to have a preferential mode, which is a liberation mode in this superconducting trap. And that's the probe system. So we modulate this external mass, and we look how basically the center of mass motion or the liberation motion is reacting to it, and that we can use to measure basically gravity, and we change the distance and the position of the source mass relative to the probe mass, and then it gives you a scaling. So interesting outcome. We measure only a fraction of Newtonian gravity, so 3/8 of the expected Newtonian gravity. So this is where our measurement is. Newtonian gravity predicts it here. So we think it's a systematic effect in the experiment. We're working on this. But in a way, that is like the interesting stuff where you want to see deviations. Yeah? So we wouldn't be brave enough now to say, Newtonian gravity fails at this point. But it is, interesting that there is a difference. But as I said, I should be careful and say that's a technical issue. It's a so-called bucket problem, and I can explain it if you want. Good. Okay, so we're planning to do more experiments and actually bring the source mass inside the cryostat and much closer to the detection system, and then we think we can, with the same probe system, we can measure the gravity of something like tens of micrograms, so we can push down to this Planck mass, and that would give us, a green star here in the gravity measurement. So if you remember, I started basically by saying this is like the mass scale. We want to have this overlap where we have both quantum mechanics in the system and gravity acting. So you saw that, quantum mechanics we can push here, gravity we can push here, so there's still 10 orders of magnitude, but it's only 10 orders of magnitude, right? So we are working on it, and I'm quite optimistic that will be happen at some point, yeah, the overlap. Just someone has to have a clever idea. It's always like that, and then it works. Good, thanks.
So we will take a 20 minutes coffee break. Is that fine? Huh? So yeah, and we assemble here at 11:35, and we will please prepare your questions that you want to ask the speakers and give it to Ritesh. Okay. So.